Hi everyone, welcome back to MATA35. This will be your second lecture, and today we're going to get started by jumping straight into some of the material. Halfway through I'll also discuss a little bit about what will go on in the tutorials today and tomorrow, so hopefully everyone is signed up for tutorials. We'll cover that administrative stuff a little bit in. But I wanted to go ahead and get started with integration because there's a lot of material to cover and I don't want to run out of time. Per usual, you can ask in chat. I am watching over it. So, last week we started doing integration. Some of you might have already seen that before in your previous class, but it's good to have some review. And one of the important things to keep in mind is that you have, just like you had with all the differentiation rules, we also have a bunch of integration rules, and they correspond roughly 1-to-1. So for each derivative rule, you have an integration rule. And I've written them all here, and I wanted to be clear about which things I expect you to know offhand and which things you don't need to memorize because I'll hand them to you. So, let's see. Everything up through the integral of sine and cosine, you need to memorize these. So you need to be able to do these offhand super quickly, because that is, these are things that will come up over and over and over again. Whereas, like, I don't even have all these memorized. So these, the more complicated trigonometric integrations, these will be provided if you need it. So I will have an equation sheet, and those, the bottom 4 will be provided, but the top several you need to memorize. And this will also be the case for the quiz. So, and I'm not saying this to force you to memorize stuff that you don't need, but just because if you don't know these offhand, you're going to find it really difficult to do some of the more involved problems, since many of the later problems in this class will require you to be able to quickly integrate many things. I mean, with integration by parts, you're often doing 2, 3, 4 integrations for a single problem. And if you don't know how to do these things quickly, then you just will run out of time. So I strongly suggest you memorize the first several. The last several trigonometric ones, don't worry so much about them. They will be provided. Okay, so now we've said that, what actually is integration for? And so let's talk about one of the big standard problems for integration. So last time we defined it as sort of the opposite of differentiation. But there's another nice interpretation, which is an area under a curve. So now if we had, let's just start with something simple. So if we have a curve that is a straight line, let's have a straight line at some value h, and we're interested in knowing how much area there is under the curve between that straight line and some value between 0 and some value b. So this area is really easy, right? This area under the curve, well, it's just a rectangle, and we know that the area under the curve is equal to b times h, the base times the height. There are some other easy examples we know. So for example, this one's slightly harder, but let's suppose we had a half circle. So this is, let's say this is a semicircle. So pretend that's half of a circle. I'm not very good at drawing them. We want to know how much area is in here, and let's say that this goes up to r, and this is r, and with a diameter of 2r. Oh, there's a question in the chat. Yes, I will be uploading the complete notes after the lecture as well. So for those of you who weren't here early on, I uploaded a incomplete version of the notes as a PDF file to the website, so you can follow along and write things down. But if you don't want to or just want to compare notes later, I will have all this available as well. Yeah, so this is also pretty easy. You know that the area under the curve of the area of a circle is pi r squared. This is half of a circle, so this is 1/2 pi r squared. And there are a couple other easy shapes. So let's just catalog one more easy shape. So suppose that you had a line. Let's say it's a straight line starting at the origin, and we're interested in how much area there is. Let's say this goes over to b and it goes up to height h. Well, how much area is here? Well, this is just a triangle. So if it's a triangle, then the area under the curve is equal to 1/2 of the base times height. Okay, basic high school geometry. But what if I gave you something harder? Let's say, let's draw some squiggly line, and I want to know the area under the curve to some value here, and how much stuff is here? And the answer to that question is a lot harder because, well, we don't have an easy formula for that. So there are a couple different ways you can try to approximate that, which you may have seen before. The let's see, area under a curve is a question mark. And you might guess, because we're talking about integration today, that integration is the way we'll get these areas, and that would be correct. So, but in order to do that, let's first talk about some simpler approximations. So we're going to talk about Riemann sums and the trapezoid rule. So it turns out that we can approximate. Oh, the very bottom of the screen gets cut off by the bottom bar sometimes. Okay, good bottom bar? Sorry, I don't actually see your screen, so if someone could drop a screenshot of that into chat, that might actually be helpful so I know like what you can't see. But yeah, I'll try not to use the very bottom of the screen. Okay, so we can approximate area under any curve by dividing into shapes we know how to compute for. So if we have, let's say we have some shape we want to measure between A and B. And let's say that we have some squiggly curve. Let's do, it starts before A, and let's say it does this. Okay, so what are ways we can compute this? There are a couple different things you might imagine. One of them would be, well, if you could divide them into rectangles, you know how to compute the area of a rectangle. So let's say that we divide it into, let's say 4 rectangles. And we take these areas. Okay, so now there's a slight problem with doing this, right? Because if you divide into these rectangles, you're still missing some of these areas here. Actually, I drew that wrong. Let me fix that. So what you're doing is you're taking a rectangle starting from the second point. So that's there. And you're missing some area. Here, 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 here. And there are a couple different ways. Yes, exactly. So this is leading up to the definite integral. So there are a couple different ways you can do this. So one is you can draw rectangles, and so this would be a Riemann sum. I'm also going to briefly mention the trapezoid rule, because that's the thing that was reinvented by the physicians that I mentioned at the beginning of class last time, which gives you a slightly better approximation. So let's see, let me get my curve again. Oh, that's not exactly the same per curve, but hopefully it's close enough. We have A, we have our B here. And so we divide them into 4 rectangles again. But then instead of just dividing up into 4 rectangles, we add a little triangle right here. Oh, we add a little triangle. And because we add those little triangles, there's actually much less area that we're missing. So here we're only missing this small area here, 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 and here. So this is the trapezoid rule, and it gets you a better approximation. So that is one way of getting a better approximation. So one way to reduce error is by choosing better shapes. And let's give an example of that. Let's give an example using a rectangle, just to give a very concrete example. So let's suppose that we have a very simple function. Let's say we have the function y equal to x squared. So let's see, 0, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the x-axis, this is the y-axis, and we have a curve that goes up. So you all know how to draw parabolas. That's 1, 1, 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have this area, and we want to approximate it. Okay, so we can try to approximate it using these rectangles. And of course, this will overcount it, but that's probably fine, right? So here we're going to call this distance delta x. So we're going to have delta x be equal to 1, which is going to be the size of the base of our rectangles. And as I said, we know that f of 0 is equal to 0, f of 1 is equal to 1, f of 2 is equal to 4, and f of 3 is equal to 9. And the area here is actually approximately equal to 1 plus 4 plus 9, which is equal to 14, because each of these rectangles, the base is 1, and so you just multiply it by the height of the rectangle, and this is 1, this is 4, and this is 9. Now this is an overestimate, but it still gets you something. Okay, so now let's try it out. So what I want you to do now is I want you to approximate the Riemann, the area under the line y equal to x between 0 and 4 using a Riemann sum. So first, let me ask you to use two rectangles and tell me what the answer is. So let's draw that out while you guys try to compute it. So the line y equal x, let's see, 1, 2, 3, 4, 1, 2, 3, 4. And this line looks something like this. And let's say that we have two rectangles. So we have this rectangle, and we have this rectangle. So what's the Riemann sum approximation of this area? One, two. Please give your answer in chat. Okay, so it looks like everyone's guessing B. So why would this be B? Well, let's take a look. What we have here is, let's see, 2 plus 8 is what people are saying. Well, what is the area? Oh, wait a moment. I drew that wrong. Sorry. That is my mistake. So this is the line y equal to x, and I just drew the line wrong. So let me do that again. 1, 2, 3, 4. So that's actually, because this is the line y equal x, so it's actually that. So feel free to change your answers. That was my mistake in drawing there. But yeah, so what you'll end up with here is you'll end up with 2 times 2 plus 2 times 4, which is equal to 4 plus 8, which is equal to 12. But of course, that was my fault because I drew it wrong. Yeah. Okay, so now let me ask you to do it with 4 rectangles, and let's see what you get. Before you, let me reset this. And then I'm going to have 4 rectangles. So, well, we can do the same thing over again. So let me try to draw it better this time. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. And the line goes up at 1, 2, 3, 4. And let's see, I was using blue for that. So we have this box here. Then we have this box, and this box. So this is going to be equal to 1 plus 2 plus 3 plus 4. Which is, of course, equal to 10. So those of you who've been answering 10 in the chat, nice. Okay, so let's go on to the next one, which is what is the actual area? So this should be super easy because this is just the area of a triangle, right? So again, 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4. Let me reset that before. Yeah. So that's an area of a triangle with base 4 and height 4. Okay, yep. So this is equal to A because 1/2 times 4 times 4 is equal to 8. So now one of the things you'll notice is that as we have more rectangles, you get closer and closer to the right answer. And so let me write that down. So another way to decrease the approximation error is to use more rectangles. And let me redo that a little bit more generally. So if you have just an arbitrary curve, let me do, say, this one again. And let me draw it twice because we can show what happens when you have... Be helpful if I could draw the same curve twice, but that is not within my skill set, unfortunately. Yeah, good enough. So now what happens when you divide this into 4 regions? So well, then you have this rectangle here, this here, this here, this here. But if you divide it into more regions, so say instead of just 4, we divide into 8 regions, you end up with something that's a bit closer. And we can write this out a bit more formally. So if we let, so the rectangles go over the line. So what we're doing is we're building a rectangle from the second point of, so each rectangle has a first point and a second point. We're going to build the rectangle from wherever the second point is, and sometimes that goes over the line and sometimes that goes under the line. Yeah, so let me write this out. So in this case, we have let delta x be equal to 1/4 of b minus a, where this here is our a point and this is our b point. Say this is a and this is b. Well, what we can do is we can let each of our delta xi's be equal to a plus I times delta x. So this here is a is equal to x naught. This point here is x1, this is x2, this is x3, and this is equal to x4. And you can do the same thing over here, though I'm not going to write it out entirely. So delta x be equal to 1/8, because we want 8 rectangles separating that we use to build up this sum. Let's see, this is 4I in 0, 1, 2, 3, 4. And here it's let xi be equal to a plus I delta x for I from 0 through 8. Okay, and here we can take the area is going to be equal to, well, approximately equal to, the sum from I equal 1 to 4, since we have 4 rectangles, of delta x times f of xi. And here the area is approximate. Using the first points it will also give an approximation that has roughly the same error, but it depends on the exact graph. So it won't give the exact same approximation because some graphs might be skewed in one direction or the other. But overall, the general point is that as you increase the number of rectangles, you get a better approximation. And that is true whether or not you use the first points or the second points. Yes, I am recording. So just to mention, I'm not using the Zoom recording. I'm recording my screen. So if there are problems with seeing the very bottoms of the slides, like they will be visible in my recording. Okay, so now that we've done that, we can decrease the approximation error by using more rectangles. Well, now, you guys have all had limits, and the natural thing to do is to take infinite rectangles. So if we take the limit as the rectangles become infinitely thin. So let's draw out that again. So I'm just doing it one more time because it's important that this is something you guys are aware of. Since this is one of the basic ideas in integral calculus. So we have some curve, and we have a bunch of rectangles. So let's say this is A, this is B, and let's say we have some number of rectangles. And this is going to be equal to x naught. This is going to be equal to, well, xn for however many n we take. And what we're going to do is we're going to let delta x be equal to 1 over n times b minus a. Yeah, I'm actually going to redo that notation. So perfect question, Samantha. Yeah, so what we're going to do is we're going to have delta x, which is going to be this distance. So the width of one of the rectangles is going to be delta x. And we're going to divide up the distance b minus a, so that's we start at the point b, we minus a, so that's the distance between a and b. So that's going to be the size of our bases of the rectangles. And what else we're going to do is we're going to let xi be equal to a plus ix delta x for I equal to 1, 2, 3 through n. So what does that mean? That means that we have x1, x2, x3, x4, x5, etc. all the way through n, and each of those is going to be one of these points here. So this point here, that's going to be x1, and so on. And the very first point is x0, and the last point is xn. So then what we can do is we can define the integral from a to b. So this is the definite integral of f of x dx. So I'm going to use this notation. It's going to be very evocative because it's going to have very similar flavor to the indefinite integrals that we were dealing with last class. So this is going to be the limit as n goes to infinity, so as our rectangles become infinitely thin, of the sum from I equal 0 to, let's I equal 1 to n, 1 to n of f of xi delta x. So you note here that we are using this dx notation to mean an infinitely thin delta x. So I'm not going to be too rigorous in defining what I mean by infinitely thin, but you can think of it as a really tiny itsy bitsy slice. And then you're taking the value of f of x, and then you're summing that together. Did that answer your question? So, let me erase some of this just so I don't. Yeah. So I rewrote this in text. So basically what we're saying is that we can define a definite integral. So I'm just taking this definition out of thin air. And what it is, it's going to be the sum of the area underneath with infinitely many tiny rectangles. So tiny slices. Any questions about that? Okay. So let's go ahead and give another example because this is, well, super important. Come on. Oh, that just erased half of my writing, didn't it? Okay, I will fix that for the actual slide, but let me turn off eraser mode and go to the next slide. Okay, so now we have a, let's give one more Riemann sum example before we move on. So, let's see. So we're taking the integral from 0 to 4 of x squared dx. Now, I'm going to assume that we don't know anything about the indefinite integrals we did last time yet. So this is a completely separate way of understanding integrals. And so we can't just use this anti-differentiation rule. And so let's try to actually solve this by taking the limit as n goes to infinity. So, well, we have our x squared. So that's going to look something like that. And we're going to draw a bunch of a bunch of rectangles. And each of these, this distance is going to be delta x, and we're going from 0 to 4. And we're going to have the delta x's get smaller and smaller. Okay, so let's write this out. So we have delta x is going to be equal to, well, we're going from 0 to 4, so that's going to be 4 minus 0 divided by n, which is 4 over n. So what this means is that we have x naught is equal to 0, x1 is equal to delta x, which is equal to 4 over n. x2 is equal to 2 times delta x, which is equal to 8 over n, and so on. And xi is equal to I times delta x is equal to 4i over n. Okay, so once we have all that, let me just erase. Okay, so once we have all that, let me put this in a box because we're going to write to the side of it. So let's say our function f of x is equal to x squared. Then what we have is we have the sum from 1 to n of f of xi times delta x. So that's the definition. So now that's equal to the sum from I equal 1 to n of f of 4i over n times 4 over n, because it's the size of the slice, right? And when you substitute in 4i over n for x squared, so this x is the same as this 4i over n. So what you end up getting here is you get a sum from I equal 1 to n of 4i over n squared. Oh, can you explain how you got the equations from x0 to xi? So that's part of the definition. So remember, we had a definition here. Oh, could I slow down a bit? Yes, thank you for reminding me. So the idea here is that we have this definition where we are defining each of our xi's to be each of the individual points that separate the boundaries of the rectangles. So here, what you would have is you'd have this here would be x1, this 0 would be equal to x naught, this here would be x2, and so on. So basically, what position along the x-axis does the rectangle end? Okay, so once we have all that, what we get is, so this is 4i over n squared times 4 over n. You can rewrite this, and this turns out to be equal to, whenever you have these sorts of sums, you can take anything that doesn't have an I in it out front by in terms of multiplication. And so this is equal to 4 over n cubed times the sum from I equal 1 to n of I squared. Why is it 4i over n squared? Isn't it 4n squared times I? So so you're talking about this step here. So what you're doing is you're plugging 4i over n into x squared, right? So this thing goes into x squared. So f of 4i over n is equal to whatever is inside of the parentheses squared. Yep. Yeah, no, thanks for asking. Questions are good. Okay, and one of the other things you may or may not remember, but you might have done some of these infinite sums in your prior calculus classes, and it turns out that we know what the sum from 1 to n of I squared is. I'm not going to rederive it here, because that would take a while, but so this is just equal to 4 over n cubed times, and this is n times n plus 1 over 2n plus 1, sorry, times 2n plus 1 over 6. This is, if you don't remember this is going to be super confusing. You should look up infinite sums again from your calculus classes. But this is one of the facts that you should know from your calculus class. So this is equal to, when you multiply this out, 32 times n plus 1 times 2n plus 1 over 3n squared. And so now we can finally talk about the actual integral. So the integral from 0 to 4 of x squared dx is going to be equal to the limit as n goes to infinity of this big thing, 32 times n plus 1 over times 2n plus 1 over 3n squared, which is equal to, by using limit properties, 32 over 3 times the limit as n goes to infinity of n squared plus 3n plus 1 over 2n, sorry, that's 2n squared, and that is just an n squared. So this is just all multiplying things out. But of course, what you end up with is, if you have n over n squared, the limit as n goes to infinity, the bottom n squared is bigger. And so this limit is just equal to 2/3. Or sorry, it's just equal to 2, since there's 2n squared over n squared. So this is equal to 32 over 3 times 2, which is equal to 64 over 3. Okay, so that was all probably a little bit confusing, especially because we had to deal with all these limits. So now, what I will be discussing in a little bit is that it turns out you usually don't have to do this. So I'm showing you this because this is how you would do it if you didn't have the fundamental theorem of calculus. Once you have the fundamental theorem of calculus, everything becomes easier. Before we get to that, though, we need to talk a little bit about something called signed area. So the definite integral, what we've talked about here, gives a signed area which is positive when the function is positive and negative when the function is negative. So on all the previous examples, we've only been talking about the positive parts of functions and looking at the area underneath it. It turns out that we often, so let me give an example. If we take the integral from -1 to 1 of x cubed dx, well, this is going to be, if you draw out this function, this is going to look something like, if you zoom in a lot, it's going to look something like this, where this is 1 and this is -1, and it is an odd function. And what we have here is we have negative area down here, and we have positive area up here. And so this is what we mean by signed area. So when the function is negative, well, it's giving a negative area, and so when you add these things together, this is actually equal to 0. Because the negative area and the positive area cancel out. This doesn't matter when your function is entirely positive or entirely negative, but it does make a difference when you're taking the integral, because effectively what you're doing, if you think back to the sum, if your rectangle ends in a negative place, then you're summing something negative times the width of the rectangle. And so you end up with this signed integral. So let's, I'm just going to check to make sure that you guys have some vague understanding. So I'm going to draw something, and I'm going to ask you if it's positive or negative. Oh, I keep on drawing over my lines. So let's suppose we had something like this. And we have all this area. And we have some negative area here. Let me reset. So would something like this be positive or negative, that integral? Yeah, so it looks like everyone's answering A, and it's obviously positive because there's more positive region than negative region. And the same would be the case if you had, the opposite would be the case if you had more in the negative region. And so you're adding all these things together. And now that we've defined sine area, we get to the most important, well, it's called the fundamental theorem of calculus, and it really is the most important theorem in integral calculus, at least. So there are two forms of it. So basically, but before going into the definition, the intuition is that we had this definition of a integral as the opposite of a derivative, right? And we have this separate definition of an integral as the area under a curve. The fundamental theorem of calculus says that the two are really the same thing. And this is why we use the same notation. We still use the squiggly s notation for both of the integrals because they're actually very closely related to each other. So in terms of the actual wording, so we have a continuous function, and if we take an integral of it, then the derivative of the integral is equal to the original function. So this is basically just formalizing what we talked about initially. So the derivative, can you guys see my mouse? You guys probably can't see. Do we have to know how to use the previous method that doesn't use, you guys can't see my mouse again. Give me a moment. Sorry. What about now? No, you definitely can't see that. Now? Okay. I'll just circle it. That's fine. Okay, so basically what we're doing here is we're taking the integral and then we're taking the derivative. And when you take the integral and the derivative, what happens is, well, they cancel each other out. So you'll notice here that we took a definite integral and we had this bound here. So we're taking the integral with respect to this variable t, but then the top bound was an x. And when you define it this way, basically what you're doing is you're measuring the area from some point A to this value x, whatever it is. When you take that integral, you get some other function, right? Because as you change the value x, you have a different sized integral. And then when you take the derivative of that new function, you get your f of x back. And so this is the first form of the fundamental theorem of calculus. So it's just formalizing the idea that the integral and what's the difference between a definite integral and a normal integral? We'll be getting to that in just a moment. And that is very important. So the basic idea here is if we take a definite integral and you take a derivative, you get their opposite actions. So integration is the opposite of taking the differentiation. We also have a second form, which is sometimes a little bit easier to use, which is that if you have a continuous function and you know what the derivative is, so you know that g of x is an antiderivative of f of x, then the definite integral is just equal to the value of the antiderivative minus evaluated at b minus minus it evaluated at a. Okay, so that was probably super confusing, and we're going to take some time and give examples of that because that was super confusing. So let me erase that, and let's talk about it a little bit more. So note, we have a indefinite integral, which is something like the integral of f of x dx is equal to some function. We can call it g of x, plus c, right? And the c here is an unknown. And that's because when we take this indefinite integral, there are infinitely many antiderivatives that all differ by a constant c. But now, whenever you're taking a definite integral, let's see, definite integral, let's say the integral from a to b of f of x dx, this is equal to some value g of b minus g of a. And so what we're doing is these two effectively correspond to each other, and so you're selecting c is equal to minus g of a and x is equal to b. So basically, when you're doing a definite integral, you end up with the actual area under the curve. When you're doing an indefinite integral, you end up with some function that, for some value of c, is the area under the curve, but that determines basically your starting point. Does that sort of make sense? So there's this close relationship between the two of them, where if you take the indefinite integral, you end up with some constant that varies. Whereas when you take the definite integral, you are specifying that constant by using your limits, by using the limits of integration. Let's give a couple more examples before we move on. Okay, so if we have the definite integral, then we don't have to worry about the exactly. So the definite integral encodes the initial value problem into the limits, and so that's the basic idea there. Whereas the indefinite integral, well, you don't know. Like, remember we had that slide where we showed that with the indefinite integral, you could like scale it up or down by some constant number. So the definite integral is from some point A to some point B. What is the area under the curve, appropriately signed? The indefinite integral gives you some function that, if you subtract from each other, would also give you that thing, but you need to solve for the initial value problem. Okay, so let's see. I think going a bit too... Okay, anyway, so let's give a couple examples. So if we have d dx, so if we're taking the derivative, so this is one of the various notations of derivative, of the integral from 0 to x of t sine squared t dt, well, that is equal to x sine squared x. And so this is the fundamental theorem of calculus, form 1. Okay, and you'll note, be very careful about the variables that you're using. So in the fundamental form of calculus, form 1, sorry, that should be a 0 there. Just to clarify, we won't have to know how to do an integral using the traditional method. If by traditional method you mean doing the really complicated limits, very rarely. Like basically, if you can do an integral by taking an antiderivative, yes. So this is an important question. Why did you use both t and x? And let's talk about this a bit more. So the reason we use t and x is because if we have some function, I'm not going to draw t squared as sine t. So let's say here what we have is we have a t-axis, and we have some function f of t, which is t squared sine t squared, sine squared t. And if we do something like that, right? What you're doing here is you're taking the integral from 0 to some value x, where x can move around. So you're taking all this area, whereas if you moved x over to here, then you take all this area as well. And it's important that you be able to manipulate these different variables. So this dt here means that we're taking a very small rectangle along the t-axis. And so when you do a definite integral, one of the things you can't do, or that you shouldn't do, sometimes people will do it, but it's a really bad form, is to do something like 0 to x, x squared sine squared x dx. Because then, which x's correspond to which? So you're integrating over this x-axis, but you also have some value x that you're integrating to. And so that just doesn't make sense. So you have to be careful when you're using the definite integral to make sure your limits don't reuse the same variable as the one you're integrating over. And of course, you can use any variable name you want. So like this could be a, b, c, d, alpha, beta, aleph, anything you want. Traditionally, people normally use x, y, and t as their variables, and you just need to look out for which variable you're integrating over, because that's the axis you're integrating over. So why did you switch to x when you rewrote it? Let me just be clear. Don't do this. That is bad. And what happens here is, okay, so let me actually write it out a little bit more clearly. So what's happening is you're taking it once you've gone from, I'm running out of space, but that's all right. So remember, when you have some function integral from 0 to x of some function f of x. Oh, sorry, I should be using t there. So let's say that's f of t dt. If the antiderivative of f is some function g, then this is equal to some function g of x minus g of 0, right? So that is by the second form of the fundamental theorem of calculus. So that is by using this here. So when you take this derivative, you substitute in for the x whatever the limits are. So here they were a and b, but of course you can use the variables however you want, and here they were 0 and x. And so you end up with this g of x minus g of 0. And what you can do then is, well, once you've done that, if you're taking the derivative of this, so this is d dx of this thing, so that's equal to, let me write this out a little bit more. This is d dx, the derivative of g of x minus g of 0. But now, g of 0 has no x dependence, and so when you take the derivative, this is just equal to g prime of x, and the fundamental theorem of calculus says that this is just equal to f of x. Okay, so just be careful about switching variables. Usually you'll see these variables be x, t, or y, but what you need to do is you need to watch out for whatever variable we're using there to determine the integral. Sometimes you might also see me write an integral even more clearly by saying the limits in terms of x and t. So that was 0 to x. You might even see me say t is equal to x to t is equal to 0. So if I want to be super clear about what variables we're using. So the idea here is that our integral is always over some axis, right? And so sometimes that's the t-axis, sometimes that's the x-axis, and we'll always specify what that integral is over by using dt or dx. So that's what we're doing here. And sometimes, if I want to be super duper clear, you can also mention that in the limits themselves, but usually you understand it implicitly because the integral corresponds to one of the dx's or dt's. Okay, so lots and lots of math. Okay, again? Yeah, sure, of course. Could you clarify a bit more what you don't understand about it, since I'm not entirely sure what part? The basic idea here is just that you can use variables however you want. You can use a variable x if you're integrating over the x-axis. On the other hand, if instead of using, if you had, I'm running out of space here, but if you had something that was an x and y-axis, then maybe then you'd use dx because you're integrating over some area underneath the curve against the x-axis. So you should always keep track of which variables you're using for the integration and which variables you're not. Now, this is only the lowest lying, I guess. Okay. Yes. So let me explain the lowest lying again. So the idea here is we have some function, this function here, which we know is equal to some function g of x minus g of 0, right? So that was part of the fundamental theorem of calculus. If g prime is equal to f of x, then this is true. And what you're doing here is you're taking your f of t, and you're replacing the value of t with x first, and then with 0. So that's why you have g of x, and you have g of 0. So it's g of x minus g of 0, and then you're taking the derivative of that entire thing, right? So if you're taking the derivative of the entire thing, well, the derivative of g of 0, well, that's a constant as far as x is concerned, because you're taking the derivative with respect to x, and so you end up with just g prime of x, which is then equal to f of x again. And so that's why you have this thing here. All we're saying is that you can reverse integration by taking a derivative, and you can reverse derivative by taking an integration up to a constant factor. This is just all formalizing the idea that integration and derivatives are the opposite of each other. Okay, so let's move on because we're and you should, if you continue having questions about that, that would be a really great question to ask your TAs. But we need to get through a little bit more material. Okay, so now let's give a biological application because you guys are mostly biologists here, and let's see how we can use this sort of idea. So suppose that we know the growth rate of bacteria in a petri dish. So some of you who've worked in the intro bio labs will have done this, and they grow at some rate. And I'm not going to teach you how to compute that rate yet. That will come later in this class. But let's just say that the rate happens to be 100 e to the minus t, cells per hour, where t is time in hours. So I want to determine how much the population increases from time t equals 0 to time t equal to 2. Well, all we have to do is we just have to take an integral now. So if you take the integral from 0 to 2, because that's in time in hours, of 100 e to the minus t dt, that will give us the amount that the population increases between time 0 and time 2. So this is equal to, remember, we can take the 100, since it's a constant, out in front of the integral. That's one of the properties of integrals. So that's 0 to 2 e to the minus t dt. And so remember, the fundamental theorem of calculus says that all you have to do is you have to take the integral, the antiderivative, and then take that antiderivative from 0 to 2. So this is equal to 100 times, the antiderivative of this is minus e to the minus t. So that should be something that by the end of this class you can just do at the snap of a finger. If you can't yet, you need to practice the integration tables. And this is from t equals 0 to t equal to 2. And what that means is we're going to substitute in t equals 0 and t equal to 2. This is 100 times minus e to the, let's substitute in t equal to 2, minus 2, minus minus e to the minus 0. So we're plugging all those things in. When you plug those things in, you get 100 times, well, this is equal to 1 because it's something to the 0th power. And so you end up with 1 minus e to the minus 2. And if you take out your calculators, you'll find this is about 86.466. And so this is in cells, because our original function was in terms of cells per hour, and we've integrated over time, which was in hours, and so we have 86.466 more cells. Now, obviously, this is just a model, because you can't have 0.466 cells, but it's still a model that gives you a good approximation of how many cells are, how many more cells there are after time, after 2 hours. Okay, so having said that, let me give you guys a problem. So, corn. So, I am from the state of Indiana in the United States. We grow a lot of corn. One of the things that corn needs is corn needs about 1 to 5 inches of rainfall or watering per week. Now, suppose that it rains today between noon and 1 p.m., so the rain's about to stop, at a rate of f of t is equal to 2 minus t squared inches per hour, where t is the number of hours since noon. So did it rain enough that you do not need to water your cornfield this week? And the possible answers are yes, maybe, no, or no clue, or more question marks. So let me go ahead and get you started on this word problem. So what you need to do is you need to take the integral from 0 to 1 of f of t dt. And that will give you the number of inches of rain. So I'll give you guys a moment to work on that. If we have to give a final answer to one of those questions, would you round down to the nearest whole, i.e. nearest whole bacteria? So that really depends, right? Because you're a biologist, and one of the things you recognize is that there are some things that are just not biological. And it depends on the application. So for example, for the rainfall example here, well, you don't need to round down because you can have fractional inches of rain. But if you can't have fractional bacteria, then what do you do? And the answer is, well, that's just one of the limitations of the model. And you would have to decide based on your application whether it makes more sense to round up or down. But it honestly probably doesn't matter because models have errors. Why is it f of t that you start with and not f prime of t that you start with? This is because f of t is the rate. So I've defined f of t as the rate of rainfall, and we're integrating over time to see how much total rainfall we have. So f of t here, oh yes, can I reset? Let's reset that. Yeah, so this is just a notational issue. So sometimes you want to use f of t, sometimes you want to use f prime of t if you have some function f of t that you're taking the derivative of. Why is it not showing up? Oh, there it is. Okay, it just took a moment for it to update. Okay, and we can do this, right? Because let me just work through it quickly. The idea here is just that this is equal to the integral from 0 to 1 of 2 minus t squared dt, which is equal to, well, if you take the integral flat, you just take the antiderivative. That's 2t minus 1/3 t cubed from t equal to 0 to t equal to 1. You plug those numbers in. When we plug in 0, it's all just 0. So this is just 2 minus 1/3, which is about 1.667 inches. So you are done watering. Yep. Okay. So this is how you might actually use these things. You can use these integrals to find areas under curves, and that's one of the standard ways, the prototypical ways that one uses an integral. Okay, so it is now 50 minutes past, and one of the things I like to do in these 2-hour-long classes, because I know that I certainly get tired after staring at someone on Zoom for an hour, we are going to have a break until 1:10 p.m. So I'm going to actually stop recording now, and we're going to have a brief break, and then we'll come back to this in another 9 minutes.